Welcome to another RDWorks Learning Lab. Today may be the start of another saga. I don't know. Hopefully we're going to be able to solve this problem in one session. We're going to revisit a subject that I accidentally keep bumping into at various stages while I'm doing my experiments. And that is the annoying problem of ripples in the background of things or ripples in the foreground of things. For example, we were always concerned about marks, vertical marks this way, when it came to doing this 3D engraving a long time ago. If you remember when we did this text, you may be able to see them in the background there. We've got something that I call curtains. We had a serious ripple in the background. Again, vertical lines. And this came to a head when I set up some little test pieces, so basically some grayscale swatches that would engrave different depths for different shades of grey. And I was doing this at different speeds. Before we talk about the grayscale, let me just point out something here that I discovered when I was busy hunting for dots. I had this pattern of 20 pixels by 10 pixels that were arranged on a grid that was 100 pixels per inch. I was trying to work out whether or not every pixel had its own signal, and here is a picture that clearly proves that every pixel has its own pulse. That's what I believed until I actually had a look at the signals and found that there were no pulses in the signals. So where do these pulses come from? Instead of 50 millimeters a second, we run that same pattern at 200 millimeters a second. Here's what happens. All the pixels disappear. They merge together. And my assumption was that because they'd become sausage shaped, they'd all merged together. Well, sausage shape was really the wrong way of looking at the problem, because it would appear that something else was going on. Now, acrylic is a fantastic material because it evaporates on contact with sufficient infrared radiation, and basically what it means is that we get little burns in here which are directly proportional to the power that it can see. We were only using fairly low power here, but look at the spikes and peaks that we were producing. So we're asking the question, where are these patterns coming from? When we start speeding things up, here's what happens to the pattern. Not only does it get smaller because the power is in the same place less time, but of course if we take a look at the frequency, we'll find that the frequency of these has changed as well. And then we move even faster, up to probably 400 millimeters a second, no, 200 millimeters a second, sorry, and we find that we've now got virtually no pulses at all. We've got some little teeny weeny peaks there, but virtually nothing. And then when we run at 400 millimeters a second, well, it's completely flat. So what on earth can be going on? Now, many people have suggested to me that it's the stepper motor. Well, where's the stepper motor in here? There are no pulses in this pattern. Yes, there are pulses in that pattern, but they're a different frequency pulse to those in that pattern, and they're a completely different frequency pulse to those in that pattern. Because we're working with a stepper motor that's basically got 200 steps per revolution, then if we start running the stepper motor faster, the pulses will get faster, and sure enough, that is what we're seeing here. It doesn't account for silly things like these strange double pulses that we're getting on here. You can see the way in which we've got one pulse followed by another pulse. And then as we get faster, yeah, look, we've still got the same sort of thing. We've got one pulse followed by another pulse. Oh, we've got a long one and two short ones, a long one and two short ones. So we've got some strange patterns occurring. I've got to believe that the stepper motor is the root cause of this, the root cause of this. But changing the stepper motor, changing the frequency is unlikely to make any major difference to this fundamental problem. Now, I'm not going to go and put my theory forward at the moment as to what's going on. What I'm going to do is we're going to have a few little games. I'm going to give you a demonstration. For those guys that are not familiar in any way with servo motor theory and control systems, I'm going to give you a little demonstration which hopefully is an image that will stick in your mind throughout what I'm going to say later on in this session. Because these fairly crude experiments that I'm going to carry out, and I use the word crude advisedly because they are definitely not sophisticated experiments, they're here to demonstrate the basic principles. Okay, now here I've got a lump of steel with a hole in it. And here I've got a stick that is marked off in increments of some sort. Now here I've got another stick that's marked off in the same increments. And let's imagine that those are steps in a stepper motor. Now I'm going to be the stepper motor itself. So the first thing that I'm going to do is I'm going to start at 0. And I'm going to say, right, let's put one step onto the stepper motor. Yeah, we've moved a step. What's happened to the load? Nothing. Let's move another step. What's happened to the load? Nothing. Let's do another step. What's happened to the load? Oh, it's moved one. Let's do another one. It's moved another one. Do another step. Nothing happened. And another step. Nothing happened. And one more step. Oh, and all of a sudden we get a big jump. So, I don't think it's going to take a genius to say, yeah, but you're using a piece of elastic here. It's not surprising that this thing doesn't work. You can see that now that I show you. That is one of the basic problems with any servo system. Elasticity. You are the perfect servo system. You've got something here, with your eyes, which gives you complete feedback of what's going on. Now what I'd like you to do to prove this is put your fist up in front of you at arm's length, and now as quickly as you can, with your fist, touch the end of your nose. Okay, now you can do that. This time I want you to close your fist, arm out, and close your eyes. Now, before you close your eyes, what I want you to do is to take your hand as close to your nose as you can, and then open your eyes and take a look where it is. That's if you don't hit yourself in the face beforehand. So here we go. And I've stopped about probably half an inch from the end of my nose. Now, even without these feedback, I've got knowledge in my brain about the position of my nose relative to my shoulder and my arms that I can guess where my nose is. Now, this one with your eyes is called closed loop feedback, where you know exactly where this is at all times and you bring it forward, and just before you hit your nose, you stop, you slow down and you just gently touch your nose. You don't come forward at full speed. You come forward at full speed and then you just stop and creep onto your nose. Now that is how a perfect servo system works. Some servo systems work this way, where if you want them to get there quickly, you go, oh, oh. Basically you have one overshoot, which basically is that. But when your nose is in the way, you can't have an overshoot. The human body has got the ability to perform like a perfect servo system. This is far from perfection. Now it gets even worse and start running at some sort of speed. Let's do 1, 2, 3, 4, 5. So I've stepped 5 pulses there quickly, and I've only moved 2.5 pulses, 2.5 down at that end. How can we improve the performance of this system? This is a stepper motor system and there is no feedback. The control system says, I want you to move 5 steps. I moved 5 steps, but the load didn't move 5 steps, it only moved 2 3/4. And the load doesn't know that it hasn't moved 5 steps. On this machine here, which is the light blade machine, we have something called a servo. To be honest, it's not a servo. The motors that are on that machine are still stepper motors. It's a stepper motor driven system, but the steppers have got a special addition to them. On the end of the shaft, they have what they call a rotary encoder. So instead of just telling the stepper motor to move 50 steps and sending out 50 signals and assuming that the motor has moved 50 steps, the controller sends out a demand for 50 pulses. But what it's not doing is just leaving it at that. What it's doing is counting the pulses that come back off the rotary encoder. So it will never do what we've got here. If I want to move 5 steps, basically what's happening, if you can imagine an eye on here watching these marks, and that's what basically the rotary encoder is doing. So although the stepper motor will be issued with a number of pulses that it's expected to give, which is say 50 pulses, it'll give a pulse, 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 and it'll say, right, okay, I've had enough pulses now, but I'm still not where I want to be. I want to be 5 marks, and I'm only at 3 marks. So let's carry on. And now it says, okay, I've got there. So regardless of the number of pulses that the controller has to put out, the command string will not stop until my lump of metal has reached its appropriate point. Now that's the difference between the system on this machine and the system on that machine. This is slightly more intelligent, but at the end of the day it's still a stepper motor driven system with a degree of intelligence, whereas this one is just a stepper motor system with 0 intelligence. How do we make this system better? Because obviously it's no good like this. Okay, so now it's pretty clear that we've got something which is now a lot stiffer. This is still elastic, look, but it's a lot stiffer. So when I ask for 1 step now, once I've taken the, let's call it the backlash, the slack out of the system, when I ask for 1 step, I'd get 1 step, and I get another step. But you'll still notice that there's some give and some stretch in the system. Okay, so I'm getting the right answer, but I'm not getting it absolutely perfectly. So again, elasticity is the killer. Now look, I've got a very thin piece of steel rod here. So I'm sure you can guess what's going to happen when I put this in the system. Okay, so I've now got my steel rod in the system, and of course if I move 1 step, I get 1 step. If I move 2 steps, I get 2 steps. And whether I move fast or slow, this will always do what this asks it to. So here is the stepper motor that's providing steps or motion of some sort, and that motion will be directly transmitted without any energy absorption or elasticity into the load. And now I get a perfect control system. So the answer is 0 elasticity. Now I'm no basketball player, so please excuse me if this goes horribly wrong. Everybody knows what this is, and everybody understands you can't do this with a ball. You have to make sure that the frequency with which you bounce the ball is constant, because you are reacting to the bounce of the ball back at you. You've basically set the ball into something called resonance. Every time the ball bounces, it squashes. And the squash then causes the ball to rebound up, whereby you hit it again and drive it down. And so, provided you do that at a constant frequency, then the system works. You can hit it harder, and if you hit it harder, you compress it more. And if you compress it more, it comes up quicker. And so, consequently, you can increase the speed of bounce by making the bounces harder. Now, again, the point about this is elasticity, absorption of energy and giving it back. Now, the reason why I'm going into all this trouble about explaining some of the basics of servo theory is because the electrical designers that design servo systems do understand things like this, but they are not generally in control. It's the mechanical guys that are providing, number one, this magic link here, and that could be in the form of shafts. It could be in the form of chain drives. It could be in any sort of drive mechanism. But this system here is not under the control generally of the electronic servo system designer. He can design the perfect servo system and it will act like a heap of brown stuff if the mechanical guy doesn't do his job right. Now, I know you're going to say that this has got a huge amount of friction in it, and that's the main reason why this thing, if you like, is so exaggerated. Yes, it is exaggerated, but any system will have friction in it. It's just the degree of friction. Let's have a bit of a closer look at our machine and see how all this stepper motor stuff that I've been talking about and how this energy absorption is somehow related to our machine. Here's my lump of metal. Okay, now unfortunately, because the belt is connected to the stepper motor, if I like to move it, you'll hear the little clicks, and you can feel the little clicks of the stepper motor. Okay, now I've got two magnets here in a clamp, and I've had to put them in a clamp because they're the wrong polarity to stay next to each other. They're not good neighbours, but I need them to be like that because basically a stepper motor is doing something like this. It's attracted to that pole there, and then it jumps across and leaves that one and sticks to that one instead. So it jumps discrete intervals between poles inside the motor, and that's what you can hear, and you can feel that resistance as the poles are attracted to each other. These bearings on here are relatively friction free, but there is still friction in this system, and there is still mass in this system. This is an aluminium head, but it still has some mass. It's much smaller than my block of metal on the floor, and the friction is a lot less, but the principles are still the same. Now, look what we've got here. We've got a piece of elastic here. Now, here we've got a very crude diagram of this timing belt. Now, along the back of this belt, buried in here, we've got a load of strings. Now, those strings could be made of all sorts of materials, but when I burnt the belt on here with my Chinese pizza oven, I discovered this. There were glass strands in the belt. Yes, these glass strands are getting closer to my rod of steel in the servo system model. So we might not have too much stretch in there. It looks like a fairly stiff system that's been designed here, with one weakness, and that is these teeth. Now, I hope you'll be able to see this, but when I turn that belt over like that, and I show you that these teeth, look, they're just rubber teeth. They're extremely resilient. Can you see that? Those teeth are actually doing exactly what this tennis ball is doing. They're absorbing energy and then giving it back. And I do believe that those teeth are actually the root cause of all the strange shapes and problems that I've been seeing. I don't think it is the belt. I think the belt might represent 10% of the problem, but I think 90% of the problem represents the teeth themselves, the resilience in the teeth. Now, timing belts are a fantastic invention. They were originally designed for transmitting power, and they replace chains and also gear trains. Now, the whole point is that when you're transmitting power in one direction. And as such, if these teeth distort in any way at all, it's always in one direction. And it doesn't really matter because you're transmitting power, you're not transmitting motion. In our particular instance, what we've got oscillating motion in two forms. First of all, in the form of going in one direction and then the other with our scans. And so consequently, we've always got the risk of a small amount of backlash at the end of the stroke when we change direction. And that we've seen when we do a scan and we get scan lines that look like this. Now, that's the main reason why we're getting these scan line problems. So come back to the fact that it was designed for transmitting power in one direction only. And yet here what we are, we're actually trying to transmit loads which are, first of all, oscillating. And yet here we are down at the stepper motor level, we're transmitting loads which are actually very, very micro oscillating loads. So, yeah, it's doing a pretty good job, but it's not the perfect solution. Now, I don't think there is such a thing as a perfect solution, except probably a shaft drive which has got a totally backlash-free ball screw system on it. It's way too complicated and too expensive for a machine like this. This is a very cost-effective solution, and it's a 99.99% solution. So, you know, we can't complain about the design of this. How am I going to go about proving that? In an earlier session, I said that I was trying to organise an accelerometer that I could fix onto here that would plug into the oscilloscope and tell me clearly that what was happening to this head every step was... Yes, I did buy the accelerometer. I don't have it anymore because I've sent it back. It was great for measuring small impact stresses like that, but these stresses here, these G-forces, relatively speaking, are not very high. And I was just unable to see the extra motions that were occurring in here over and above the noise that was in the accelerometer itself. So that was a total failure. I've now got to find a different way of proving to you guys that the fundamental problem here is resilience and resonance. Now, resonance is a strange phenomenon that happens in electronic systems, but particularly in mechanical systems. Okay, so we've made our own little resonance gauge here. It's pretty crude, but it should do the job. Now, what we've got here is a mass which slides backwards and forwards along this bar. And technically, this length here is like when we were bouncing the ball. You had to bounce it at a certain height to get the frequency of the bounce right. Well, that's what's happening here. So if this end is moving in little teeny weeny steps, what it's doing is pulling this end of the bar away and making this end move. And this end will move, but there's a mass on it. So this end cannot move at the same speed as that because, look, it's elastic. And so what will happen is when this frequency here becomes sympathetic with this length, this mass here will go into oscillation. Maybe only a small oscillation, but hence what we've got out here is an indicator so that you can clearly see what is happening. So we start off with it very short, and then of course what will happen is any vibrations that take place in here will be like sounds in an organ pipe. You will get strange resonances in here. So this thing will just wobble at a very, very high speed, but it'll show that there's vibrations happening in here that are driven by this unit. And as we increase this, what we should find is that we'll reach a point where this no longer goes at very high speed. What it'll do what it's doing now. It will actually go into an oscillation as it's travelling along. Now what I've got to do is to stop it from oscillating for the very first accelerating period, and so that it's basically stable, and then we can see what's happening to it once it's travelling along its stroke. All will become clear when I start playing with it. Okay, well, I've tuned this now, and we'll run this first of all at 10 millimeters a second. Now just make sure that it doesn't wobble before we start, so I'll just hold that until it's going, and then I'll let go of it and make sure it's nice and steady. So it's lost its vibrate, it's just vibrating gently now. And now it's gone into oscillation. Now it's stopped. Now it's gone back into oscillation again. Now it's stopped. And back into no, can't quite make up its mind. Now it's oscillating again. Quite violently, as you can see. Here we are at 20 millimeters a second. Let's see if we can stop that. Nice and steady. And there we go, it's starting to build now. Start, stop, start, stop, start, stop. So it's picking up some harmonics there. Now 30 millimeters a second is a completely different sound. But it's still going into oscillation. Steady oscillation. Now it's stopped. Now it's off again. Nice and still. Oscillations. 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 All the way along, oscillations. Gentle motion. In fact, 40 was worse than 50. 60 millimeters a second. Lots of vibration. No oscillation. As it gets faster, it's going to be more difficult to control it. There we go, that's still. Ah. Now it's gone into oscillation and stop. Now, here we are at 80. We got some good results at 40. Maybe double the speed, we should get some good results at 80. Nothing. So this is 90. No, I think as we get faster, we really don't have enough time for anything to seriously develop. So we'll try 100. Oh, we're developing something at 100. Yeah, this is a bit of a hit and miss principle. It works, but I'm not so sure it's going to be entirely accurate in telling us the results. I think we're going to have to rely more on the results in acrylic, because these do not tell lies, these are completely repeatable. So all I've got to do is first of all repeat this test to make sure that I can see my pixels. They're not really pixels, but see if I can see this pattern of dots at 50 millimeters a second. If I can, then I know that I've got something that's completely repeatable on this machine. And when I make a change, if I see a change to this result, well, you know, we know that we've definitely affected the performance of the machine. Now that's my little black phantom pixels, and yes, they are still there. But now we know better. When we saw the oscilloscope signal, we saw switch on, do 10 pixels or 20 pixels, switch off. And then, as far as power is concerned, what we saw is the power switch on from nothing here, sit level, and switch off. In fact, that was wrong. We didn't see that, because what we then saw was the signal turn round, come back, and do another scan. So in other words, it went one way, then the other way. So there was one scan of 20 pixels. It then turned around and did another 20 pixels, and the power remained constant all the way through, and it wasn't until the end of the program that the power stopped off and went to 0 again. So there was nothing in the oscilloscope signals for these 20 pixels that said on, off, on, off, on, off, on, off, like that, which would have caused that pattern. But because we had a flat pattern, where do these come from? Well, the answer is something that I've been talking about quite a lot and often, and that is that this head is not moving at a steady speed. Well, look, I'm just going to, it's totally out of focus, but let's just do a pulse. And there we go, we've got a pulse. And at the moment that pulse is, it's probably about halfway through. But if I leave it in the same spot longer, not only does it go through, it's burnt the paper underneath. The point that I'm making is the depth of this burn is related to the time of the burn. So the longer the burn stays in one place, the deeper the hole becomes. Now what we should be seeing is a cut that starts here, goes in, and like that, and stops. But what we're seeing is a cut that does this. So in addition to the fundamental power that we've got here, which is giving us the cut depth, we're seeing additional power taking place because we've got a deeper cut. We can't have additional power because the power is steady throughout the cut. So the only thing that can be causing this is the cut is stopping, and that's allowing the burn to go deeper, and then it's accelerating and moving on to the next position. So as it accelerates and goes quickly, the cut stops. Bearing in mind the beam is on all the time. There's no propagation for this beam. It's on continuously. So what we're seeing here basically is a track in the acrylic of speed. And the deeper the cut, the slower the speed, and the shallower the cut, the faster the speed. And so this cut here is going quickly stop, quickly stop, quickly stop, quickly stop. It's moving across here in a series of jerks to produce that pattern. It's just an amazing coincidence that at 50 millimeters a second we happen to produce 20 pulses to match my 20 pixels. I mean, I should have done the lottery that week, shouldn't I? So we do some more tests. Because this, I think, is probably about the best record that we're going to have of the machine condition now. We'll carry out the same series of tests afterwards. And yes, at 10 millimeters a second we have our same pointy pixels. And 200, believe me, is nothing more than lines, although there might be just the merest hint of, I can see some changes in the line thickness, so possibly there are 2 or 3 ripples in there. So we'll just do one last test at 400, and those are definitely nothing more than lines. So we'll have a look at those under the microscope so that you can see what we've got. Well, here's 10 millimeters a second, 30 millimeters a second, 50 millimeters a second, 100 millimeters a second, and the pattern's disappearing, 200 millimeters a second, and it's virtually nothing there at all. And 400 millimeters a second is just flat randomness. And I think that's enough by way of a simple set of tests to now carry out the major change that I'm going to make to this machine. What is the major change? This belt is different in two ways. Now this is made of a material called polyurethane, which is a much stiffer material than the rubber that's in here. So not only is it a slightly different tooth form, it's also a different stiffness of material. But the other big difference between this and that belt is that this one has got steel cords in it. When we look on the end there, there's a whole load of steel cords that run through this belt. So there are several ways in which I think that this belt will be stiffer. Okay, well that was not too bad to get the belt fitted up. Probably 15 minutes work. That wasn't very difficult at all because, as I said, I'd already done this before. Now, we've still got to reset this head now because I've just bolted it back on into a nominal position, but it's going to have to be set up in the correct position so that the beam can go up, pass in and go down through there. We've got to do that because we've got to retest the machine using our acrylic. Before we get to that stage, what are we going to expect? Well, that will be a surprise, but it would be good to have a logical projection of what we are expecting to see based on fact that we do know. When you make things stiffer, you actually improve the response relationship between the driver and the load. So on that basis, because I've stiffened this system up and I've taken away the sponginess in the system, technically I'm going to see here what's happening at the stepper motor. So I am actually going to see steps here. Now, does that mean to say I've made the system worse or better? Well, we'll have to make that judgment call when we see the results. But one of the things that people have said to me is that it must be the stepper motor, because from the results that I have had before, as the system gets faster, the frequency changes, which is what you'd expect from the stepper motor. That's an immediate conclusion that you would jump to, but when you stop and think about it, that is totally untrue. Okay, let's try and make some sense of my scribblings on this sheet of paper. My pattern that we're going to test again is 100 pixels per inch. That's the black pattern that we used as a reference. Now that meant that every pixel is actually 0.254 of a millimetre wide. Now, my pattern is made up of 20 pixels. So therefore the total length of my pattern is 5 millimetres. Now, let's just make an amazing assumption that my stepper motor, which is 200 steps per revolution, happens to travel 0.254 for every step. Now that means it's going to take 20 steps to travel across this pattern. Notice I say 20 steps. If the stepper motor runs at 1 revolution a minute or 2000 revolutions a minute, it's still going to take 20 steps to move across this pattern. So there isn't a frequency change in the pattern dependent upon the speed that we're running the test. And the real test that we're looking for this time is that we can see 20 steps across this pattern as we move up the speed scale, because really what we're doing now, we're actually linking the head with the stepper motor more directly, and so consequently I'm expecting to see these little patterns extend up the scale, if you like, but I don't expect them to keep changing shape as we get faster. We'll now just pop my little gauge that I made, which checks the center position of the beam. So we're a little bit low, so we've got to drop the head down just a fraction. And here's a precursor to why I've made the head adjustable. I don't have to go and set everything, I can just move this head down slightly. Up just a shade. So we could just bring the head out. Okay, now that I've lined my beam up on the entry, we'll just do a quick check here to make sure things are lined up as well. So we just do a quick pulse there. And we'll drop it down. See what we've got. Not far out, but it could do with coming back that way just a shade. Bit more. Too much. Pretty good. Check. We'll raise it back up. Not bad. That's pretty well lined up. Made things a little bit easier for myself this time. I've included the cutout in the test program. So the first test is 5 millimeters a second, 10% power. And I've purposely cut the shape close to the pattern so that we can get a good view under the microscope of what's going on. 40 millimeters a second. The first thing is take a look at the bottom left hand edge and also at the top right hand edge of the pattern, and you can get an idea of the depth of cut. Now, superimposed on that depth of cut, we've got these, what I suppose are motion spikes. Now, this is right down at 5 millimeters a second, where I would expect to see every single step of the stepper motor. Now, the second pattern at 10 millimeters a second is similar, but to be honest, there are a few less spikes in here. The depth of cut's about the same, but yeah, it's not completely uniform. 20 millimeters a second? Wow. The spikes are beginning to disappear. 30 millimeters a second? Well, the spikes are disappearing very much. Well, with the exception of those little spikes at the end there, that's a fairly flat pattern. That's a bit unexpected at 40 millimeters a second. There's a lot of them and they've all of a sudden appeared back at 50 millimeters a second. Wow, look at that at 60. So we've got something going on there. 70. And 80. All of a sudden they've just disappeared. 90. 100. Virtually nothing there at all, just fairly flat. 150. One or two little spikes occurring back again there, but nothing dramatic. 200, flat. 250, flat, with something strange happening in the middle there, but basically flat. 300, a little bit of choppy waters there again at 300, but again nothing diabolical. And 400, strange. Look, we're getting a little bit of a reoccurrence of those spikes again. So we'll just check out my little Waggle meter test. Right, well, this is 40 millimeters a second. A lot of noise, obviously vibration going on, and yes, we're generating some resonance there. That's at 40. Now maybe that noise is actually the micro stepping holding the motor back. Well, at 50 millimeters a second we've got a completely different sound, and we're starting to get some vibrations. Now remember, 50 millimeters a second was where we got our peaks starting to come in, our speed peaks. 60 millimeters a second. Well, they're starting to go bonkers at 60 millimeters a second. 70 millimeters a second. Not much going on there, is there? 80 millimeters a second. Very little going on there. And also the sound is very smooth. Let's go back to something like 10 millimeters a second, and let's just listen to the stepper motor. We can definitely hear it vibrating. 20, 30, 40. And 50. Now we're into smooth mode. 60. 70. And 80. We can hear almost what we can see on our pictures. 3 sound phases. We've got this very strange and vibratory sound up to about 40 millimeters a second, and then the stepper motor changes to a much smoother sound from 50 millimeters a second upwards through 70. I can hear some of the more seasoned engineers amongst you saying, yeah, but that vibration's not from the stepper motor, that's from this loose bit here. That's going into resonance. What do we think now? The sound is emanating from that stepper motor just there. What conclusions can we draw from today's session? I think the point is proved that the rubber belt has got absorption characteristics, which this belt does not have. We've got a much stiffer system here, and I'm getting a better translation of the steps from the stepper motor into the load here, into the head. In some ways that might be bad, because we have a very specific zone now at between somewhere in the region of 50, 60, 70 millimeters a second. We're definitely getting these stop-start motions in that head. But at the really slow speeds, and once we get above about 80 millimeters a second, we've got a pretty smooth characteristic. Well, I think we'll terminate today's session on that slightly inconclusive note. Now, before I do the next session, I will do some preparatory work. I'll check out the pulley that we've got on here. I'll check out the stepper motor speeds and micro steps. I'll do measurements on the acrylic patterns to see if I can work out what the pitch of those motions is, to see if we can somehow relate them back or prove that they are the stepper motor. I think I've got enough information now to come to a conclusion. But in the meantime, maybe I can get some feedback from some of you guys that understand exactly how micro-stepping works. I mean, the evidence of what we've seen today is that from the sound and from the speed traits, it would appear that there is a zone of control for micro-stepping, and then it moves out of micro-stepping into full stepping, and then probably from full stepping it stays on full stepping, but we're getting inertial effects which damp out the steps. But who am I to know? This is yet another speck in my wide spectrum of incompetence. So any help will be very useful. Until the next session, thank you for your time.